All right. Last time we left off talking about the Church-Turing thesis, universal computability, the notion that there's many systems that can compute, not just our silicon-built devices, but they're all over nature. There's DNA computers, gravity systems, cellular automata can compute, water pipes can compute. It's quite phenomenal. So computation is all around us. You know, some physicists say that the whole universe is one big simulation or computation, and from some point of view, they're not wrong about that. So we went through some simple things to compute, games and puzzles. They're not efficiently computable, but they're computable nevertheless, and they're computable pretty well using heuristics, chess, even Jeopardy, lately Go have been conquered as things we can compute. Cars are beginning to drive themselves around the road. Within 5 years, most cars will be self-driving, or at least the new cars will be all self-driving. It'll be amazing. It's all about algorithms. And there's fewer and fewer things that humans can do that computers still can't. Every year we lose one or two things that we thought is strictly in the domain of human capability, and such as self-driving cars and many other things. And then we started going sort of from the low end of what's doable, computing primes, computing digits of pi, graphics, animations, and then we started getting into things that are kind of fuzzy, humor, emotions. Those are hard to quantify, much less compute or simulate artificially. Things are hard to predict. Hurricanes, earthquakes, tsunamis, chaos comes in very quickly. Insufficient data is always an issue. Even if you had all the data and there was no chaos, undecidability lays on top of all that and still makes it a very hard problem to deal with. Anything to do with human behavior, such as elections, diffusion processes, turbulence, all very heavily laden with chaos, very high sensitivity to initial conditions. And so these things may be forever uncomputable, at least very accurately. So, we said that weather is not the same as climate. Climate is easy to predict. Hot in summer, cold in winter. But that's not a simulation. That's just an aggregate statistic of what is true. So from Navier-Stokes equations, we still can't predict crashing waves on the beach. So there's a disconnect between our equations, which we know are correct, and the actual phenomena that we observe, photograph, paint, and write poetry about. It's all embedded in the equations, but not in an obvious way. Okay, so those things are hard to compute. And then we gave an example of a very simple chaotic system, double pendulum. It's probably the simplest example of unpredictability, undecidability, and chaos that I can think of. It's just in 2 dimensions, there's 2 degrees of freedom, and it goes randomly, apparently, even though the equations are very well defined. They're right there in differential form. Pretty amazing. And then we sort of ended up mentioning fractals, and today we pick up on that. So fractals are fractional dimensional objects. They can be defined recursively, although they don't have to be. And there's lots of examples all over the place in nature: trees, clouds, coastlines, snowflakes. These all have fractal properties. In movies, they're used heavily in generating animations and interesting effects in terms of graphics. Here's a fractal dresser, chest of drawers. Geometric expansion is a fractal table. So those are kind of interesting. Fractal patterns on yarn. Fractal tattoos. Don't go out and all get one all at once. But they're very, very ubiquitous. So here's a fractal antenna. Why would you want a fractal antenna, by the way? These antennas are embedded in your cell phones right now. Your cell phone has typically fractal antenna that have this kind of geometry, hierarchical fractal geometry. Why do you think that would be advantageous from an electrical engineering point of view? Yeah, the geometry of it, if you want to pick up very small wavelengths, this piece of the antenna will do it. Larger wavelengths, this aggregate piece will do it. Very large wavelengths, this piece will do it here. So the same antenna is not restricted to pick up one narrow band of wavelengths, but rather can pick up a large range of different wavelengths. That makes the antenna much more universal, ubiquitous, capable about a much wider spectrum of signals. So it has applications all over the place, including in electronic design, and you're carrying them in your pockets right now. Fractal geometry objects. There's a company called Fractal Antenna Systems. In fact, they make these fractal antennas for the cell phone makers. They also invented an invisibility cloak, a lot like the Harry Potter one, except it's a lot more primitive, of course. You can't wear it. But whatever's inside here becomes invisible because light comes in, and this thing directs the light around the object and puts all the light out from behind the object. So if you're over here, you're seeing the light source and not the object because it all goes right through, which by definition is what makes something invisible. So it's not quite the cloak that Harry Potter wore. Boy, he looks really young in that one. And it's not quite the cloaking device that Captain Kirk tried to steal from the Romulans back in the day. I don't even know what I'm talking about. Any Star Trek fans here? Okay, well, your mileage may vary. But it's amazing that we can come up with cloaking devices, and we used to think it's just pure science fiction or fantasy movies like Harry Potter, but we're beginning to build those, actually. So one of the most famous fractals is the Mandelbrot set, defined very, very simply. You basically take a point in a complex plane. This is a complex plane, x and y, x plus I, y, complex numbers, and you start squaring it. Square it at a constant, then square that at a constant. It's recursive squaring, basically, iterated squaring and adding a constant. Any number that you start with, that once you square it at a constant, square that at a constant, keep going, ad infinitum. Any number that you keep doing that to, that goes to infinity, that diverges, is outside the set. Any number that stays within a bounded distance from the origin is inside the set. That's it. That's the definition of the Mandelbrot set. But it's said to be the most complex object in all of mathematics. And that's saying a lot because there's some pretty complicated objects out there in math, including very large, complicated groups and so on. And it looks beautiful, and it's a fractal. It's self-similar. If you start zooming in on the Mandelbrot set, you see more and more and more copies of the whole thing, slightly skewed and warped. How many have seen the Mandelbrot set in animations? Good. So it's not hard to compute this thing. It's very simply defined. It just has an incredible level of complexity and structure and detail and beauty. And people have been investigating that for a few decades since it was discovered by Benoit Mandelbrot, the researcher, the mathematician at IBM that first defined that set and investigated its properties. But again, it has chaos. It has undecidability, and perhaps even incompleteness properties based on Gödel's theorem. Some things about this set are true, but we could probably never prove them because there's no proof for these, even in theory. So just thought I'd mention it when we talk about chaos. And here's some animations, again, zooming in, orders and orders of magnitude. And as you keep zooming in, you see more and more copies of the set itself in slightly warped configurations all over the place. Very intriguing phenomena from such a simple equation. It's squaring. So again, we see how a quadratic already gives you chaotic, unpredictable, perhaps undecidable kind of behavior simply from the act of squaring, never mind cubing or taking to higher powers or doing more complicated functions as just a polynomial even. The minute you go nonlinear, all bets are off, basically. You're in very, very deep theoretical, mathematical waters. And of course, there's fractal art. These are all computer-generated art. There's competitions every year, art competitions, where all the entries are computer-generated, produced by algorithms. How many knew that? No human entries. And these are all algorithmic art. And some of it's very, very sophisticated. This is already several years old. Today, they're even more sophisticated than what you're seeing here. So you can create like insect-like creatures and so on, simply from a few lines of code involving fractals, typically. Here's a few more examples. I'm going to flash a bunch just so you see the diversity and sophistication of computer-generated art. So, 10, 20 years ago, we thought, only humans can do really good art. Computers can do a few simple, kind of simplistic animations and that kind of thing. No, now computers can generate very interesting, deep, great art. And again, keep in mind these examples, some of them are 5 to 10 years old. Today it's a bit more. So you can see the Mandelbrot set, for example, right there. That's the shape of this lake over here. And some of it is more telling as to where the fractals are that generated some of these art. Others, it's hard to see the fractals. You just see some interesting abstract art. If you put any one of these in the Museum of Modern Art on a big canvas and say, you can have this for $1 million, some people will buy it. If you tell them it's a computer, they probably won't buy it. But so it's a perception, but it's pretty amazing. Flash a few more. Some of them are animated, others are static. You can sort of see where you have fractal kind of behavior, self-similarity. And fractals can occur in any dimension, not just two, and in other spaces, not just Euclidean. It's a whole field of study. Hundreds of books written about them. People are getting PhDs every year studying these objects and their relationships, their properties. Again, more computer-generated art. Here you can see like a 3D version of a Mandelbrot set. That one's pretty obvious. But others, not so much. So this is fascinating. If you show it to an average person, 50-50 chance to be able to tell it's a computer or a human. Most of them will say it's a human, actually. So it's more than 50-50. So again, this is just a small sampling of the ability of algorithms and computers to generate what we would consider pretty good art, maybe modern art or abstract art. And of course, you can also generate Renaissance-type art with Madonnas and cherubs and that kind of thing. It just won't look as cool as this, but it'll look very much like the works of Raphael and Michelangelo and Da Vinci. So it's not just abstract art, it's other art too. I'm just showing you the fractal type of computer art here. So if you want to read one good book about fractals and chaos theory, if you ever saw Jurassic Park and you heard this mathematician guy kept ranting and raving about chaos theory as he was being chased by velociraptors, then read this book right here, The Fractal Geometry of Nature by Mandelbrot. It's a great place to start. It's written by the author who invented the Mandelbrot set. And then, of course, there's a few others. They're all on the website, or at least several of them are on the website. It's on the reading list. You can get extra credit. It's pretty cool. So the Church-Turing thesis, wasn't meant to be computable. That's where we started. That's where we're ending on this. Basically, it says that a human, us, can do basically what all of these other models of computations can do, including a Turing machine. And all these are equivalent via reductions back and forth, so they're lumped together. A human can even use prosthesis for their brain, abacus, supercomputer, whatever. Doesn't change anything because a human can only do it faster with a computer, but not different. Right? It just gives you speed, but not superpower to have a prosthesis such as an abacus or a computer for you to use while you think and contemplate and figure things out. And so the thesis, again, is that a human is equivalent to these other things. And it's not demeaning, it's not insulting to say that a human is equivalent to a Turing machine. It just means a Turing machine is pretty darn good. It's a high compliment to a Turing machine, not an insult to a human. I want you to understand that. Any questions about any of that? Or the implications or the philosophy? It's pretty interesting. People are still looking at it, thinking about it. There's various variations of this thesis. People wonder if quantum computers might be able to do things that a regular computing device couldn't, or maybe even that a human couldn't. And some physicists even say that a human might rely on quantum phenomena to be able to do what we do, from the very low level of electrons and protons and atoms jiggling about, doing quantum things that then affect nerve firings, that then affect our thoughts. So maybe our thoughts and our perception of what it means to be conscious and aware and sentient may have to do with quantum phenomena. Some people make that argument, and they're not people off the street, they're informed scientists. It's not a majority opinion, but could be true, in which case, we may not be a mechanical Newtonian type of deterministic algorithm or mechanism in our brains. We may rely on true randomness and quantum phenomena and Heisenberg uncertainty principle and a whole bunch of other interesting constructs from quantum physics and who knows what else. It's possible. People are still looking into all these things. Of course, now we have quantum computers, so computers can also rely on quantum phenomena. So maybe quantum computers can match our quantum intuition if indeed that's what we do as conscious beings, unbeknownst to us consciously, because it's all part of the physics that makes us up. Any other thoughts, questions about any of this? It's pretty deep stuff. It's philosophical. Right? A lot of loose ends, a lot of fuzziness about it, but it's fascinating. Yeah. So here I am contemplating all that in Musée Rodin in Paris. This is where Rodin has his famous thinker, the original, not the replicas. So it's a lot to think about. It's pretty cool stuff. All right. So switching gears, resource-bounded computation. So up to now in this course, we basically were pondering what's possible and what's not possible for a model of computation, whether it's finite automata, push-down automata, a Turing machine, or whatever else, what it can do and what it can't do in an absolute sense. So a finite automata cannot recognize 0 to the n, 1 to the n. There's no two ways about it. Create a bigger one, more complicated one, it still can't do it because it's context-free but not regular, 0 to the n, 1 to the n. So no finite automata can do it. Now we're going to switch gears and talk about how fast something can be done. Not whether it can be done or not. We assume it can be done, and we know it can be done, but how fast can it be done using a finite automata, push-down automata, Turing machine, an algorithm, whatever the mechanism is. So now we're going to start splitting hairs, and things will get more dicey. Because it's not just about whether we can or cannot do something, but how efficiently can we do it. And there's a whole range of possibilities there. It's not a binary anymore. It's not a binary decision or option. So we're going to measure time and space. How much time or computation steps, and how much space, that is, room on the tape, do you need, or RAM in memory, or memory in general. And those are interrelated, but they're not the same thing. Right? So we're going to start measuring things in time and space. So if a language is decidable within time big O of t, t is a function, n is the parameter. It's decidable within time t if there's a Turing machine or an algorithm, it's equivalent, that decides this language always within that time. So if a string comes along that's size n characters, if you can always terminate with a yes, no, within time t of n, t of n could be n, t of n could be n squared, it could be cubic, it could be exponential, it could be factorial, it could be super exponential, but it's some function. So you can always terminate with that time t of n, the language has to be decidable within that time. So now we're putting a little caveat on decidability. It's not just any old time, no matter what. Always stop, always say yes or no. Nobody cares about the time up to now. Now we care about the time. Okay. So string comes along, size n. If you can always determine yes or no whether it's in the language or not in the language within time t of n, the language is said to be decidable within that time t of n. How many get that definition? Oh, good. So notice that, first of all, it's big O notation. It's asymptotically time t of n. It's not specifically t of n. It's any constant times t of n. So make sure you understand it's big O notation here. So 2n squared is the same as 5n squared, the same as 100n squared. It's all n squared, asymptotically. So how many know what big O notation means? Okay, good. So we won't have to harp on that too much. It means basically we don't care about the constants, roughly. All right. Similarly, analogous definition for space. A function or a language is decidable within a certain space S of n. If there exists a Turing machine or an algorithm, it can always decide it, yes or no, within that much space. No more than that much space on the tape. Or if you're talking about an algorithm, not much more space than that much RAM malloc in your C program or Java program or whatever. Right? So now so this is time-bounded computations. They have a limit in time. These are space-bounded computations. They have a limit in space. Now, if you have a limit in time, you can take all the space you want within that time limit. If you're limited in space, you can take all the time you want as long as you don't exit that space limit. Okay, so make sure you understand. If I put one limit on you, the other one is unlimited. Of course, it may be implicitly limited by the other limit. Right? So if I say you have 10 days to do something, you're time-bounded, you're time-limited. And if I say you have to do something but stay within $1 million budget, now you're money limited but not time limited. You can take a year to do it, or even a decade, as long as you don't exceed $1 million. The other one is you can only take 10 days and you can use all the money you want. You can use $1 trillion, but only take 10 days. So one bound doesn't imply anything necessarily about the other bound other than what actually could happen based on their relationship. But it's not explicitly tied together up front. Okay? So there's two different notions. And they are related. We'll see all sorts of relations between space and time. All right. So we start splitting the hair even more. So now we talk about deterministic time and non-deterministic time. So D time and N time. So just like this previous definition, we just said within time, but we didn't say, are you allowed to use determinism or non-determinism one way or the other? Same for space. Now we're splitting that hair. D time, T of N means it's decidable by a deterministic algorithm or deterministic Turing machine. N time, same thing except you allowed non-determinism. So that red N corresponds to this red non-determinism option that you have. So we're splitting that hair. We're going to split that hair also for space. So now you have D space and N space. So these two definitions are for time, these two definitions are for space. It's just whether we're allowed to use non-determinism or not. We already saw that non-determinism can buy you efficiency. Right? If you have a non-deterministic finite automata, you want to convert it to a deterministic finite automata, there's a construction, what's it called? One word. Convert a non-deterministic finite automata to a deterministic finite automata. What's the construction called? Just to make sure you remember or even listening. Anybody want to buy a vowel? I hear it, say it loud. Power set, yeah. How many know power set construction? Remember that from 2 months ago? Okay, so remember we did the power set construction. Things could have exploded exponentially. The number of states could have grown to the exponential of the original number of states, which suggests that if you allow non-determinism, maybe you could be more efficient than if you insist on determinism only. And we tend to believe it's true, and it's very hard to prove one way or the other in many cases whether that's actually a phenomenon. Because in some complexity classes, they're the same. But for polynomials, we don't know. That's exactly what the P is equal to NP question says, whether non-determinism really allows you to be more efficient by a substantial amount. All right, so now we got some hair splitting going on, determinism, non-determinism, both in space and in time. So we can measure things 4 different ways now. We can say it takes deterministic time so-and-so, non-deterministic time so-and-so, deterministic space blah, and non-deterministic space something else altogether. So now we have 4 different algorithms, 4 different bounds, and they don't have to be the same. Some of them may be the same, who knows, but it depends on the example. All right, now look at the following. These are also properties. Why are they properties? Because deterministic time is defined as all the languages that are decidable within that time. So it's a collection of languages. A language is a collection of streams. So each one of these complexity classes indexed by the functions, and there's an infinite number of functions, n squared, n cubed, 2 to the n, n factorial, and whatever else you want to make up, infinite number of functions. So you have an infinite number of deterministic time classes, an infinite number of non-deterministic time classes, an infinite number of deterministic space classes, and an infinite number of non-deterministic space classes. And each one of those classes is a collection of languages, and each collection is infinite too. And some of these languages in the collection, each element of one of these sets may be finite, may be infinite language. But the totality of languages in each one of those categories is infinite. How many get that? Okay, any questions about that? It's important that you understand the types. They're nested
4 deep now, the types. Each one of these objects I'm defining an infinite number of objects here because they're indexed by a function, and there's an infinite number of functions. So for each specific function, there's this set here on the right-hand side, and it's a set of sets of sequences of characters, 4 deep in type. Keep that in mind. Each one of these is not a set of strings. It's a set of sets of strings. Very, very different. All right. So because there are properties, what can you tell me about the decidability or undecidability of each one of those sets, each one of those infinite number of sets that I'm presenting to you on this slide? What can you tell me about them now that I've hinted to you that they're properties? Not a trick question. None of them are decidable. It's undecidable to know if a language is in any one of those sets. And there's 4 classes of infinite number of sets each. So it's impossible to know if a language can be decided in linear time, or quadratic time, or exponential time, or any other space. Because they're properties, and that makes them undecidable by which theorem? But there's a special name for that theorem. We went over it the last time and the time before that. Maybe the time before that. Rice's theorem, yeah. So by Rice's theorem, immediately each one of these is undecidable because none of them are trivial classes. None of them are either empty or contains everything. Okay. Any questions about that? So you see, we just got a free theorem falling on our lap from Rice's theorem. And that theorem applies to each one of those classes. They're all undecidable. And each one of those definitions gives rise to an infinite number of classes. And there's 4 of them, so there's 4 sets of infinite numbers of properties in each, or sets of languages in each. And they're all undecidable by Rice's theorem. So you see, things compound pretty nicely now. And we get a lot of oomph and free mileage out of Rice's theorem and previous results immediately when we define things and start looking at things. All right, so time is tape dependent. So what does that mean? The time depends on the number of tapes. So if you have more tapes, you can do things more efficiently, right? So for example, 0 to the n, 1 to the n. How would you recognize that with 1 tape? So 0 to the n and 1 to the n are on the tape, and n could be large. So you have 1,000 zeros and 1,000 ones. Let's say this table is all the zeros and this table is all the ones. And you try to determine, as a Turing machine or an algorithm, if there's an equal number of zeros here as an equal number of ones there. How do you do it? Well, we already did this simulation a few lectures ago, right? You can mark this 0, go over to the ones, mark this one, go over to the zeros, so first unmarked 0, mark that, go over to the ones, mark the first unmarked 0 there after all the marked ones, go back, find the first marked one, go over, find the first unmarked 0, mark that, go back and forth, mark and mark and mark and mark. And by the time you're done, if there's no more zeros and there's no more ones in excess of the other, you'll know that they're in equal numbers. And you can say, yes, I accept. It's one of those strings in the language. Otherwise, you say, no, I reject because it ain't. How many understand this algorithm? All right. Then tell me the time complexity of this algorithm as a function of the length of this string. Yeah. How many see quadratic behavior here? Good. Because you covered n zeros and n ones every time you wanted to erase one pair and mark a pair. So n plus n plus n plus n plus n times, that's quadratic, that's n squared. So that algorithm I just described is n squared time. So it's in d time n squared. It's in that class. It has that property. That doesn't mean it's not inside other class as well. In fact, it is. It's an n cubed. How many see it's also in n cubed time? How many see that if I can solve an algorithm in linear time, I can also solve it in exponential time if I want? Why? You're always free to waste time. In fact, let me give you an interesting natural example. Let's say I want to sort, and how long does it take to sort if you want to be efficient about it? Sorting, just plain old sorting. N items to sort. n log n. But let me give you another algorithm for sorting. Take the numbers you want to sort, create all permutations of those numbers, all permutations. See which permutation is monotonically increasing, and output that. How many see I just sorted? Yeah. How long is this algorithm in terms of time? Somebody else? Not a trick question. I gave you a perfectly valid, correct sorting algorithm, but it's inefficient. How inefficient? 2 to the n? Close. It's worse than that, actually, but it's getting there. It's not quite as bad as n to the n, but that's even closer. How many permutations are there on n objects? Not a trick question. Somebody else besides the same 5 people that impressed me again and again? How many permutations are there on n objects? N factorial. And what's n factorial according to Stirling's approximation formula, roughly? It's roughly n to the n over e to the n, but so they're very close. So it's roughly n to the n. So I just gave you a very pessimistic algorithm for sorting. It's correct. It works. It's just horribly inefficient. The point is this. Just because something is in one complexity class doesn't mean it's not in other complexity classes. In fact, it is automatically in every larger complexity class because you can always waste time if you want. Right? So this algorithm I described to recognize 0 to the n, 1 to the n in quadratic time, that language is not just in quadratic time, it's also in cubic time, exponential time, factorial time, and any other higher time limit class than quadratic. How many get that? Okay. Just make sure you understand that because you're going to go much deeper than this very quickly. Things like this will become obscure and abstract. All right. Now, that's for a one-tape machine. Everything was on one tape, and I had to do everything on that one tape. I had no second tape to work with, so I took quadratic time. But that doesn't mean it's not in any smaller class than quadratic. In fact, it is in smaller class than quadratic. If I had 2 tapes, how low could I push the time? If I had a second scratch tape over here in my Turing machine, I still want to recognize 0 to the n, 1 to the n. How fast can I do it now as a function of the length of the string n, or 2n? Yeah. I can do it in n log n. I can do it even faster than that if I had a second tape. So you're right, but let's even push that even further. Yeah. You can do it in linear time, right? N over 2 and both linear. Who can see linear time if you had a second tape? How would you do it? Not a trick question. It's pretty straightforward. You have a second tape. What do? All right, but your input is on that one tape. So what do you do with the second tape? I mean, you're on the right track, but you have to be a little more specific than that. Yeah. Yeah, you can take all the zeros and move them to the second tape, or copy them, not necessarily move, but copy them to the second tape. Then go over the zeros as you're going over the ones, and then you'll know they're in equal numbers, and you do a linear scan on both. Or you can go over the zeros and go over that tape, the blank tape, like he said. Go over the blank tape as you go over the zeros. And then if you go over the ones, you go backwards on the second tape as you go over the ones, and that's another way to measure the zeros to the ones without having to copy them. Maybe that's what you wanted to say. All right? How many get both algorithms? And there's many other ways to do it. So that language is not just in deterministic time n squared for one-tape machines. It's in deterministic time n for two-tape machines. So you see the classes are machine dependent. They're number of tapes dependent. And sure enough, if you have more tapes, you imagine you can do things more efficiently. And if you have more heads, you can do things more efficiently too. If you have a one tape but a two-head machine, you have two read-write heads. You take one head, leave it there, put the other head over there on the ones, and then advance them in lockstep, and then you'll know when you run out of zeros and ones, whether they were an equal number. That works too. So for a one-tape, two-head machine, that language is still in linear time, deterministically. How many get that one? Really? Just two people? All right, I'll repeat it. How many see that for one tape, we're talking about quadratic time? We did that 5 minutes ago. Okay, good. How many see that for two tapes, the time drops from quadratic to linear? Good. Now we're going to go one tape, but two heads, and the time will remain linear. It won't go to quadratic. Two heads start at the beginning. There's 0 to the n, 1 to the n on the table. Keep one head here on the zeros. Take the other head and walk it over to the ones. And now walk them together on the zeros and the ones in lockstep, one at a time, until you run out of zeros at the same time that you run out of ones. And then you know you got on your hands one of those, and then you can say yeses and if and only if. Now you're a decider in linear time. How many see that? Good. All right. So the bottom line is that the efficiency of the machine in terms of time depends on how many tapes it has, strictly from this example. And there's many other examples that are even more dramatic than that. Okay. Now let's prove something even more interesting. Let's show that even for a one-tape machine, you can do it not quite in linear time, but you can do it in n log n time for a one-tape machine. And one head and one tape. Not two heads and one tape. We just did that, and that's linear. One head and one tape. N log n time. Go. You need to recognize 0 to the n, 1 to the n when you see it. And you only have n log n time now. And one tape or one head, what's your algorithm? Any thoughts, ideas, hunches? How many understand the question? And that was only 10 people. Ask me questions about the question. What am I asking you to do? I'm asking you to come up with an algorithm that in n log n time, with one head and one tape, will recognize strings of this form 0 to the n, 1 to the n. Just like we did in the last 4 examples, or 3 examples. Except now I'm restricting you even further. You don't have two tapes. You don't have two heads. You have one of each. And you're not allowed quadratic time anymore. We've already been there, done that. We're taking it a step further, upping the ante. We're taking it from quadratic to n log n with one tape and one head. How many understand the question now? That's better. If I don't see a lot of hands, even when I ask if you understand the question, there's no point in going on. We just need to repeat the question a few more times. That's okay. But I want to make sure you understand what I'm asking you to do. Question or answer. Okay, so she's talking about a binary search tree. It's an interesting idea. Now, you're going to have to put the binary search tree on the same tape where all the input is. And that'll take you a bunch of time, too. Right? You're going to have to walk over, pass all the inputs, start constructing a tree over there. And that, it's not clear if that'll take an awful long time. And probably will take a bunch of time. But it's not a bad idea. It's just you have to make sure you do it efficiently on that one tape along with everything else. Because you don't have extra storage. You don't have RAM or anything like that. So you're a Turing machine. All you got is states and a tape. And the tape only has one head on it. And that's it. That's all the storage and memory you have. Any other thoughts? Thanks for saying that. It's an interesting idea. Create some data structure. And sometimes that works beautifully, actually. Any other thoughts or ideas? Yeah. We established that n squared is sufficient. We didn't say it's necessary. So for example, I'll be happy to sell you a bagel for $1 million. I'm willing to do it. So now you know that the price of a bagel is no more than $1 million, because I'll sell you one for $1 million. Doesn't mean that somebody else won't sell it to you for $10 or even $1. Does that make sense? So if nature will allow you to compute something in n squared time, doesn't mean that you can't compute it any faster, some other more clever way. Does that make sense? It's an upper bound, not a lower bound. Don't confuse upper bounds with lower bounds. We'll talk about lower bounds too quite a bit. And when the upper bound and the lower bounds meet, it's a good day. You know exactly how long or how much something takes. Like sorting. Sorting, we have n log n upper bound. It's called merge sort. We have an n log n lower bound too, so we know merge sort is optimal. But here we're not there yet. We gave two upper bounds. So it's an upper bound of n squared. Doesn't mean that n squared is a lower bound, and I'm telling you it isn't. I'm implying by asking you to do an n log n time, I'm not asking you to do an impossible task. I'll never say do something, go, when I know it's impossible. It's just rude, right? I don't play tricks like that. I may ask you, is it possible or not to do something in n log n time? But now I'm implying to you that it could go one way or the other. I'm not sending you astray by telling you something is impossible, trying to trick you. I never try to trick you at all in this course. Hope you appreciate that. I don't play gotcha with you. So I'm telling you it is possible, n log n time. Otherwise, I wouldn't be saying it. But now you got to give me an algorithm that achieves that time. And going back and forth character by character doesn't cut the mustard because that gives us quadratic behavior. So how do you get to n log n somehow? Any thoughts, ideas? Yeah. Recursion? Well, you're a Turing machine. What does recursion mean for a Turing machine? You can't even call functions, much less recursive functions. Right? You can change states. You can read the tape. You can move left or right with the tape head. That's all you can do. So we say recursion. Explain to me how the Turing machine will behave from that description. Does that make sense? It's like saying, oh, have a Turing machine text my friend. Or have a Turing machine go up to the web, do a search, and find out the answer and report it to me. Well, a Turing machine doesn't have a web server. It doesn't have an internet connection. It doesn't have a hard drive. It doesn't have a screen. It doesn't have a keyboard. So you can't just throw those in as if nothing happened. Right? Be careful. Yeah. If you'd like, I mean, you can do what a Turing machine can do, which is read a tape cell, replace that character with some other character, move left or right, and change state. So by saying, are you allowed to mark? Well, if changing a character by another character, you want to define that as marking, then yes, be my guess. Yeah. Yeah. You can mark the 0, then mark a 1, then mark a 0, then mark a 1, then mark a 0, then mark a 1 until you run out of zeros and 1s. How fast is that? That's n squared. Right? So we've been there, done that. This algorithm is correct. It's just not fast enough because it's n squared. And we're going for n log n now. But thanks for saying that. That works. We need to get faster than that, though. Yeah. Okay, so he has a variation on this algorithm. It says match the first 0 to the last one, then the second 0 to the next to last one, then next to next, the next to next, the next to next, to next to next, to next, until you meet in the middle, and then you'll run out, and then you'll know. How many get that algorithm? How many say it's correct? How many say it's n log n? How many say it's quadratic? And you're right, it's quadratic. But it's a good try. Why is it quadratic, by the way? Because the time is n plus n minus 1 plus n minus 2 plus n minus 3, and we know what all that adds up to. Remember the staircase, the blue and the red staircase that Carl Friedrich Gauss, when he was 7, was, how many remember that? You add up 1 and 2 and 3 and 4 all the way up to n, and you get quadratic. In fact, you get n squared roughly, and really it's n over 2 times n plus 1. But still, it's quadratic exponentially, asymptotically. So, but it's a good try. What else can you try? Yeah. Right. Do you know what? Well, n is implicit by how many there are, but it's not stored anywhere special other than there's n of them on the tape. Remember, the Turing machine doesn't have registers. It doesn't have RAM. It doesn't have places to store numbers per se, other than what you put on the tape yourself, you being the Turing machine. Okay, interesting. So he's saying find the halfway point of the length of the tape, and at the halfway point, make sure that the zeros end and the ones begin, basically, and then you'll know. That's a correct algorithm if you can find the halfway mark somehow. How do you find the halfway mark if you're a Turing machine? Well, a Turing machine is very restricted in what it can do. It cannot surf the web. It cannot take a square root. It cannot, not directly, right? All it can do is look at a tape cell, change its state, and move one cell to the left and one cell to the right. So with that, how do you find the midpoint? That's sort of the fuzzy part here in your algorithm. Otherwise, it works correctly. Yeah. And how do you go back that many times? You have to store the many times somewhere as a number. Where are you going to store it? In a register somewhere? Machine has no registers. You see what I'm saying? It has to work given the capability of the machine and what the machine can do, and not something special that it can't do. It's like saying, I have a program, I have an algorithm that can recognize faces, right? It has a large library of faces, photos. When it sees a face, it just matches it with the library, and it knows which one it is. End of story. How many see? That's not a complete algorithm. I haven't really described an algorithm. I described a wishful thinking approach. Because I didn't describe exactly how you're going to compare a face to another face, given that there are two different photographs. One is a little bit of a profile, and one of them is a darker shade of light. And I didn't describe all these nuances and complications. And I just said compare the two faces as if they're two integers that you can compare equality to. Faces are not. Not if you're comparing two different photographs of somebody. Maybe they're from two different times in their life, even one of them is younger, one is older, one has a beard or hat and not, and on and on and on. You have to explain all that in your algorithm. When you say, oh, I'll just compare two faces and see if they're the same. You can't just throw it out there as if nothing happened and walk away, declaring victory like you achieved something great, when you completely glossed over all the details of the algorithm. It's like saying I'm going to create a great chess playing program by having it look at all positions, see which way is the best, and make that move. There, I just described to you a grandmaster chess level program. No, I didn't. I just gave you a wishful thinking kind of a sentence that is devoid of any details and algorithms. I want to create a self-driving car by having it just mimic human driving behavior, look at the signs of the road, respect the traffic rules, and go. No, that's not a self-driving algorithm. That's wishful thinking. So tell me how a Turing machine, is going to, in n log n time, discover that there's 0 n's and 0 1's without resorting to wishful thinking. I want all the details, something that works, not just hand waving and walking away from it. Yeah. That's what a Turing machine does, one at a time. Nowhere in the definition of a Turing machine can you teleport the head a light year away on the tape. I mean, we never said that, and it can't happen. It could go a light year away by going one square at a time for a light year, and then you'll be a light year away. But not in one fell swoop and one fell jump. The machine doesn't have that capability. Just like a finite automata can't take a square root out of the blue. It just can't do that. It doesn't. It's not part of the definition. Just like in your Java program, you can't say, recognize the face of my mother, right? And walk away as if that's going to actually happen in your code. You can't just say that. Recognize my mom's face. Paren, colon, semicolon. You can type it in. It's just not going to do anything. There's no Java definition for that operation unless you implement it from scratch. And it'll be a heck of a complicated subroutine. I'm just stating the obvious, right? It's not a big revelation to you, hopefully. You've all been programming, and you know what it takes to program. You can't just state the goal and walk away and hope that it'll happen by magic. You have to go through all the grungy details and make sure that it'll work. And even that, then you got to test it and debug it and make sure you didn't leave anything out. That's called programming. So what else? Program this Turing machine for me. Show me how it works. Yeah. Do what? No, Turing machine doesn't have scissors. But, it's a good try. So I'm telling you what a Turing machine can do. It has a bunch of states, like a finite automata. It can change states. It can look at the tape cell that it's on now, and based on that, what's in that tape cell can change the state as a function of the content of that tape cell, that one cell. Once it changes states, you can move left or right. That's it. That's what a Turing machine can do. Everything else, it can't do. Not directly. Just like in a program. What can you do in a program? Can you recognize a face? No. Can you invert a matrix? No. Could you tell the difference between a dog and a cat? No. In a program, all you can do is have an assignment statement, define a variable, have a loop, call a function that, again, has those things in it, and any combinations of these things. And from those building blocks, you can build larger programs that do more sophisticated things. How many get that? All right. And so if you ask me, can a program cut up its memory into two pieces? No. You can maybe implement that effect somehow using lots of these components I just described, an assignment statement, an array, subroutine call, some looping, and so on. But you can't just say, have the program paint half its memory blue. That's not part of the language of Java or C or whatever. You have to use the primitives that are offered in the language. From that, you can build larger primitives. At this point, I feel like I'm teaching you programming, right? Like you've never programmed before. Right? And I know that's not true. I know all of you have programmed before. So let's get away from that level of detail. Let's just say, get me the Turing machine to do this in n log n time, and don't try to get the machine to do things that it can't do. Like take a big jump and land in the middle of its tape. What does that mean for a Turing machine to do that? It's not part of the definition. If it's possible, you have to build it from the primitives that it can do, so show me how to do that. If you want to get to the middle, you can. But you can't just say, just go to the middle. It's like I can't say to the Turing machine, recognize my mom. Tell your program to do that. How is the program supposed to recognize your mom? You could write an algorithm, maybe with 1 million lines of code, that will reliably recognize your mom from a photo, from a GIF, or JPEG, or a TIFF. But that's not going to be an atomic operation. It's part of your standard Java library, or definition of the Java language. I hope you get that. Let me ask you an interesting question. How many have actually constructed a Turing machine to do anything in this whole class? All right, now you're scaring me. Seriously. How many constructed a finite automata with a set of states and a bunch of transitions to do some specific thing in this entire class? Good. Okay, I feel a little better now, because 2/3 of you raised your hand. I'm still not sure why it's not 100% of you, but I'll take that. So let me ask again about push-down automata. How many constructed a push-down automata to do some specific task, whether it's on paper or using JFlat? Okay, so I see a lot less hands with that. How many did it for a Turing machine? It's only 3 of you, so let me ask you, why did I only see 3 or 4 hands raised? I mean, we've talked about Turing machines for weeks now. Why haven't you sat down and written a Turing machine to do anything? Just curious. if this was a programming course, we'd be learning Java or C or C++, and we were 2/3 into the course, like we are, and I asked you, how many of you have written a program in Java, because this is a Java programming course, and only 3 of you would be raising your hands, I'd be pretty scared too if I saw that response. But that's what you're telling me, so it's pretty weird, actually, for me. Sorry. So how are you supposed to understand Turing machines if none of you, if only 3 of you out of 150 people, have actually sat down and wrote one down? And if you haven't, why haven't you? You can do it in JFlap. I've been begging you for months to use JFlap, and JFlap has Turing machine construction in it, where you can define the states and the transitions and then simulate it on an input string and see what it does. And if it doesn't do what you want, you can debug it and so on and so on. But if you haven't done it, it's like you're in a programming course. You're listening to me. You're looking at the slides. You're learning how to program, or at least you think you're learning how to program, but you've never written a program. It's like telling me I could swim, and I asked you, where'd you learn to swim? You said, I looked it up on the web. I saw some videos of swimmers. Have you ever been to the ocean? No. But I know how to swim. I've seen other people do it. I understand what swimming is. Ever been in the water? No. But I know how to swim. It's just not credible. Sorry. So that's what you're doing. That's what you're telling me now, which is a little weird for me. Some of the exercises in the sets have to do with Turing machine. Construct a Turing machine that does this, right from the book. There's lots of exercises in the book about that. I keep telling you to work out these problems. So at this point, I think I might just put on the final exam some exercises of the form, write a Turing machine with all the states and transitions that does the following and give you some tests. I think I might just do that. Because you're not doing it on your own, and you need to know it, and you can't answer these questions without practicing it. So how about that as a forcing function to get you to do it? There'll be some final questions about stuff like this. Otherwise, I'm not sure why you're not practicing constructing Turing machines. I mean, Turing machines are just algorithms, right? They're like programs. It's like programming in assembly. It's low-level programming. But the reason you're having trouble with this example, the reason we just wasted 25 minutes on it, is because I guess none of you constructed a Turing machine to do anything. So when I said Turing machine can do this or that, you don't know what I'm talking about. And that's not good. It's not healthy. It prevents us from going forward as a group. And so help me help you, like Jerry Maguire says. Construct some Turing machines. Use JFlap, for God's sakes. It's a required thing, right? Using JFlap is one of the required assignment readings, right? Use it. Speaking of which, since we're on this tangent here, on the midterm, it was pretty obvious that some people were just copying answers that they don't even understand, either from the web or from their friends or from study groups. And, I don't want to call it cheating because, I said you can usually work in groups. You can look stuff up on the web, and that's all fine and dandy. But I think some people, even a substantial number of people, have looked up answers on the web for a lot of questions, printed it out on notes, and during the exam, you just copied down blindly whatever it is you looked up before the exam without even thinking about it, and worse, without even understanding it. And it's pretty obvious. So that's disturbing to me, and it should be disturbing to you too. So on the final, I may put slight variations of the problems from the problem set. Not exactly the problem on the problem set, but tiny variations. That if you try to copy the answer without understanding it, you'll be wrong. Okay? So we still have a few weeks left before the exam. But I've seen enough of it already, and now I'm seeing it yet more, that a lot of people are doing the bare minimum necessary to just satisfy the pedantic sort of rules that you perceive this class to be, but you're not really bothering and understanding anything or doing anything beyond just satisfying the letter of the law, but refusing to learn anything above and beyond what it takes to abide by the rules that I laid down. And that's not healthy, it's not good, and it's not impressive, frankly. It's not what you should be doing. So,
there'll be variations on questions, not verbatim exactly necessarily the exact same question. So if you think you can get by just copying answers without understanding them, you're going to have to do some more thinking, some more understanding, not just blindly copy things. This course is not about Google searching and copying blindly stuff that you don't even understand. No course is about that. So, you're forcing me to try to make an end run around your insistence on knowing as little as possible. And I'm talking about some group. I'm not talking about the whole class. So if you're not in that group, great. I love it. But if you're in that group, I wouldn't be doing a big favor if I allowed you to do that just blindly. All right. So back to this question. Let me solve it for you then. 0 to the n, 1 to the n. We don't want to go 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, back and forth, back. That'll give a quadratic behavior back and forth. Instead, I'm going to eliminate every other 0. Eliminate every other 0. Mark it. Mark the first 0, the third 0, the fifth 0. So skip a 0, mark the next unmarked 0. Skip a 0, mark the next unmarked 0. In one fell swoop, I'm going to mark half the zeros. Go over here. In one fell swoop, mark half the ones, every other one. Mark it. Go back. Now I have half as many unmarked here. Then mark every other unmarked 0 that's left. Then go over here. Mark every other unmarked 1. Go back and forth and back and forth. Keep doing this. Mark every other remaining unmarked 0. Mark every other remaining unmarked 1. How many times do I have to do this before all the 0s are marked and all the 1s unmarked? How many passes are we talking about? Log n. How many see log n here? Because I keep dividing the number by 2. How many times can you divide it by 2 until it disappears? Well, log n, that's the definition of a log. It's how many times you can divide it by 2 until it peters out, right? Question? Well, the input is 0s and 1s. But you can use other characters, right? You're constructing the Turing machine. A Turing machine has an alphabet. The alphabet doesn't have to be 0 and 1 of the Turing machine. The alphabet of the language is 0 and 1, but I never said the alphabet of the machine is only 0 and only 1, right? So now I'm allowed to use A's and B's, 0s and 1s, and A's and B's, let's say. Does that make sense? And that's okay. A Turing machine can do that. It has an arbitrary but fixed alphabet. And that alphabet doesn't have to be just 0 and 1. That a Turing machine can do. Use a larger alphabet. We give examples of machines that have larger alphabets, and you can always simulate larger alphabets with smaller alphabets. That you can do too. So the marks are just extra characters. So after log n passes, I'm going to eliminate all the 0s and all the 1s. And when I make a pass and find no more unmarked 0s, and make a pass on the 1 and find no more unmarked 1s, I know that they're an equal number. End of story. That's the algorithm. That's what the Turing machine can do. That's what it will do. And it's not calling any special functions. It's not teleporting to the middle of the tape. It just goes and makes passes, eliminating half the 0s and half the 1s with each pass as log n passes. So the total time is n log n. All right, end of story. Now, if you've never programmed Turing machines, that's why you're having trouble with these kind of questions. Otherwise, once you see it, it's pretty straightforward. So this language, 0 to the n, 1 to the n, for a one-tape machine, it's also, as well as being in quadratic time, it's also in n log n time, deterministically. OK, question? How do you know what to mark? So let's say a bunch of them are marked from before. And you need to mark half of the remaining ones. So we're in the middle of this process, let's say, inductively. But, OK, you look at me funny, so let's start at the beginning. Let's say all the 0s are unmarked. How do I mark every other one? Exactly. Mark 1, skip 1, mark 1, skip 1, mark 1, skip 1. That's easy to do with a couple of states.
Yes. So skip all the marked ones. Find the first unmarked one. Mark that. Then skip all the marked ones. Find the first unmarked one and beyond that, and don't mark that one. Then skip all the marked ones. Find the first unmarked one. Mark that one. Then don't unmark the next. Mark the next. Don't unmark the next. Does that make sense? So you're still skipping back and forth, but in between you're flushing all the marks. That's okay. You can just have a state that iterates, flushes. It's like a while loop in your program. Flush the marked ones, find the first unmarked one, and keep bouncing back and forth, iterating mark, unmark, while you're flushing all the marks in between. How many get that? That's an important detail. All right. That's how a program would do it. That's how a Turing machine would do it. And I'm still not teleporting anywhere. I'm not using scissors to cut the tape. I'm not doing anything funky that a Turing machine can't do. Okay. Question? Well, you're flushing the marked ones. You're still moving in one direction only, as you're making one pass. Right? So you're still going in this way, and you're flushing all the marked ones. You find an unmarked one, you mark it. Flush all the marked ones, find the next unmarked one, and don't mark it. And then mark the next one, don't mark the next one, mark the next one, don't mark the next one after that. And keep flushing the marks in between. So you're still marking every other unmarked one, ignoring the ones that are already marked from before. Does that make sense? Good. It's a good question. It means you're understanding it. Yeah. So at the end, one of them will peter out. Because at the end, you only have one unmarked one, and you'll be marking it, and there'll be no more unmarked ones left, let's say on the zeros. But then you'd go over to the ones, and you'll see that there's more than one left. There's no more zeros left, and maybe there's let's say you mark one of the unmarked ones, but then there's more than one left. Because when you mark the very last zero, the next time there'll be no more zeros unmarked, and you'll know that because you're looking for an unmarked one, you won't find any. And so you go into a special state that then, in the program, into a special piece of the code, where now it'll check that there's no more unmarked ones as well, that not all of them have been marked from before. And now you know they're in unequal numbers. In other words, you're looking to run out of zeros at the same time that you're running out of ones. You don't run out of zeros and have excess ones left. You don't run out of ones and have excess zeros left. That means they're not in equal numbers. Okay. Does that make sense? So that's one way to do it. There's other ways to do it too. And that gets us into n log n time. All right, let's move on. I don't want to spend too much time on that slide. So the space doesn't depend on the number of tapes. Because remember the old construction, you can take a bunch of tapes and basically merge them together using kind of a dovetailing, and you can interlace them like this. And so from 3 tapes with n on each, you can have a tape with 3n on it, but 3n and n asymptotically are the same. How many see that? N and 3n, the same, big O notation. Okay, so space, multiple tapes doesn't help you. Time, it certainly helps you. That was an example of how, using some cleverness, we got from n squared to n log n, and even to n if we had 2 tapes. Right? So if you have extra tapes, time can improve. If you have extra tapes, space does not improve. So time and space are 2 different measures. They don't have the same properties, as you'd expect. One of the reasons is that space is reusable. If you have a bunch of space that I allocate to you and you can say use it, you can reuse it and reuse it. The same space for more and more things, for different things, erase, reuse it for something else. You compute the square root in that space, erase that, get the answer, erase that, and then use the same space to compute the logarithm. And then erase that, use the same space to do addition, whatever. Space can be reused. Time cannot be reused.
Think about it. When a second passes, when an hour passes, when a day passes, you can never get it back. But if you have a room somewhere, you can fill it with different things on different days, reuse the same space over and over and over again. Utilize that same space, reuse it. You cannot reuse the same time over and over and over again. Time reused is gone forever. I'm just stating the obvious, but it's a subtle point, but it's a very deep point too. And it relates to this. A machine can reuse its space. Your program can reuse the same memory locations over and over and over again. It cannot reuse the same clock time over and over and over again. If it expended time, it's gone. It can spend more time, but it gets added to the first time. It's not the same time that it's reusing. But it's the same space that it's reusing later if that's what it chooses to do. Keep that in mind. It sounds obvious, but it's deep and it has implications for all these theorems. And for life, actually. In your personal life, you should cherish time very, very dearly because you cannot get more of it. Money, you can always get more of. I mean, you have to earn it, but you can always get it back somehow. Time, you can't get it back. You wasted it, it's gone. Rules to live by. All right, so space, extra tapes don't buy you anything. And a one-tape Turing machine can simulate a time-bounded Turing machine roughly in K tapes. So if you have a K-tape Turing machine, you can simulate it using a one-tape Turing machine in time quadratic by going back and forth, having all the tapes side by side, and basically going all over them, back and forth, sweeping them, changing each in turn, simulating each in turn for every time step of the multi-tape machine. But you have to go through the whole thing for every single step of the multi-tape machine. You have to go over the entire tape of the one-tape machine for every single step of the K-tape machine. So you end up squaring the time. I'm not going to harp too much on that. I basically said, I just explained it, but if you haven't used Turing machines, I hope it's not too obscure to you what I just said. How many sort of get it, what I just said? Okay, good. That's a lot of people. Wow, that's okay. I'm impressed. It's good. So deterministic time is always within a larger time than that. In other words, this says if you have a time t prime that's bigger than tn, these are just functions. So one is linear, one is quadratic. If you're in linear, you certainly are in quadratic. And so the set of languages that you can describe in linear time is a subset of the quadratic time and so on and so on. If you have more time, you don't lose any languages. You can just get more languages. So you get subset, not necessarily proper, but subset containments here. If you have more time, you can recognize more languages. More space, you can recognize more languages as well, right? So by next time we meet, when I ask you if you use JFlap, if I don't see almost all hands raised, when I ask you to use JFlap over the weekend, we're going to have a stern conversation again. Okay, so you should all use JFlap. Look, it's required. It's on the class website. It's marked in red. It's required. So why not do it this weekend rather than wait till the day before the final or whatever? So please use JFlap. Simulate Turing machines, simple ones. Get them to work, debug them, and then we won't have to have these conversations that are awkward. All right? See you next time. Yeah. Yeah, stay home. Yeah, stay home.
When were you planning on giving it out? Because I have exams on Saturday, Sunday, and Monday of that first.
Yeah, I would.